All right, we're going to get started. It's 7 o'clock. Welcome, everyone. I'm Carolyn Jacobs from GBH Education. We're happy to be back with you hosting webinars after a couple of months hiatus. And we are back with gusto with this one, Teach with NOVA, focusing on Earth and Space Science resources for K-12. We're hosted by GBH, which is Boston's public media station, and the producer of many iconic programs that we hope you enjoy on your public media stations around the country. Programs such as NOVA, Masterpiece, American Experience, Frontline, and lots of programs for kids. And we are also a major producer of educational resources that are published on PBS LearningMedia. We're also in the education department, we research and produce content and resources and services for the equitable learning and development of young people and adults. And we do that in part by publishing resources on this platform, pbslearningmedia.org. It's free. Many of you submitted questions in the registration form about the cost of what we were going to be showing you. Rest assured, it's all free. PBS Learning Media offers thousands of resources for K-12 across the curriculum, but we are very strong in science, and most of what you see tonight is available at pbslearningmedia.org. We are recording this session. We will send out a recording link tomorrow, along with a link to a resource document and the slides. We've captured the resource links that are mentioned, that will be mentioned tonight, into a resource document that we'll share with you. We have Angelica from the Education Department in the chat who will be monitoring things and responding to your questions. About 2/3 of you did submit questions ahead of time on the registration form, and thank you, and I want to acknowledge them. Many of them have been passed along to the presenters, and they will try and incorporate some of them into their presentations. And also some of the questions are appropriate for Angelica to respond to in the chat. Feel free to put them in the chat also. And then, of course, we have reserved from 8 to 8:15 for open Q&A. And we hope that you, the presenters, will be here for that. And we look forward to more open conversation with you after the presentation. Our presenters tonight, we've had a very good time putting this together, and hope that you agree with us that it's time well spent. Ralph Bouquet is the Director of Education and Outreach on the NOVA team here at GBH. Anjali Tripathi is an astrophysicist with NASA, and Ralph will be introducing Anjali and giving you much more information later about her. And Sean Stevens, my colleague in education, is the Director of STEM Curriculum and Instruction, and we work very closely together to plan these webinars. Then we have two wonderful educators. These are not in the order. Eric is going to be presenting first, and then George. Eric is a chair of the science department and also teaches Earth and Space Science and Chemistry at Tucson High Magnet School in Tucson, Arizona. He served as a teacher advisor on the Bringing the Universe to America's Classrooms project, a collaboration between GBH and NASA, resulting in many, many wonderful resources on PBS Learning Media, which you'll hear a little bit more about later. That was in 2017. He worked with us, and since then, Eric has been an ardent proponent of PBS Learning Media resources and has presented on several of our webinars. Thank you, Eric, and welcome. And George Hadamenos has been teaching physics in Richardson, Texas for 21 years. He earned his BS, MS, and PhD all in physics. I think he probably knows his stuff about physics, huh, George? In 2010, he was named a PBS Digital Innovator and then became smitten with public media resources and has been a strong champion ever since. This is his first time presenting on one of our webinars. We're thrilled to have him. Thank you. Welcome, George.
Thank you very much.
Good. Both Eric and George are very open to collaborating with you. They love, in particular, supporting new teachers, mid-career teachers, old teachers, any kind of teachers. So you'll have their contact information, and they would love to hear more from you and exchange ideas. After some brief introductions, we're going to be hearing from Dr. Tripathi and some fascinating information on exoplanets with gorgeous images. We'll dive deeper into the resources from Universe Revealed on PBS LearningMedia, and then hear from Eric about how the resources work with his students. Then we'll move on to Polar Extremes and the resources on PBS LearningMedia, and hear from George about how he has incorporated some of them into his unit on penguin habitats. We'll have some final announcements, and then we'll have the Q&A. Okay, we're going to get started, and I'm going to turn it over to Sean.
Thanks, Carolyn, and thank you all for joining us this evening. Happy New Year for all of those of you that celebrate Lunar New Year. I'm just going to orient you a little bit before we start and digging into the content. Once again, most of the resources that we're going to be talking about tonight can be found on pbslearningmedia.org. And they're free and should be easily accessible to you. Next slide, please, Carolyn. Within this PBS LearningMedia, there's the NOVA collection. And this collection alone has over 1,500 resources from NOVA's broadcast and digital productions. They're all organized like the NGSS standards are. So by the STEM branch, and then subtopics by disciplinary core ideas. Besides the science topics, we also have collections about people in STEM, so they're videos of STEM professionals talking about their careers and how they got there. NOVA Labs, which are great interactives where students can investigate all sorts of scientific topics. So I encourage you to check that collection out. And then these NOVA broadcast collections, we're going to dive into a couple of those today so you can see what those are about. Next slide, please. We realize that, it's not really reasonable for you to watch an entire NOVA episode in a classroom. So what we do in the education department is to excerpt the key visualizations and phenomena from episodes that we believe will support you in helping students meet key learning goals. So they may be things that can engage kids in phenomena in interesting ways, lots of different interesting problems, or address things that we know that students find difficult. The video clips are relatively short. Rarely are they over 6 minutes. If you see the timing that's longer, that's a gallery of multiple videos. So they're in separate videos, so it gives you control as to how you want to use the videos and content in your instruction. Next slide, please. The other thing that NOVA is great about is really connecting the science to current events and society. In April of 2020, they already had an episode out about COVID and developing drugs and vaccines for that. Kids may see stuff about CRISPR in the news, and there we have it. There's resources for you to talk about. So NOVA is a good place to look for you to make science meaningful to students and help them connect it to their lives as well. All these resources, besides having the videos, include teaching tips, which are just ideas for how to implement the videos in your classroom, as well as discussion questions. And some of them often also come with background readings to provide you with support for unusual technical content. Since last season, we've also been including handouts, which engage kids more deeply with the media and engage them in science practices. So that's just an introduction to all of the NOVA resources, and we'll be talking more about them more in depth later on. So I will turn this over to Ralph now.
All right. Thank you so much, Sean. Welcome, everyone. Thank you so much for being here, for spending your evening with us, talking about NOVA's resources and really how you can best implement them with your students in your classrooms. So I just wanted to talk very briefly and just do a quick introduction in case you're new to NOVA education, just to let you know what we're all about. And so essentially NOVA, and actually, Carolyn, can I switch to sharing my screen?
Sure. A second.
Okay, great. Thank you. All right. I'm going to add that. All right, here we go. Okay, great. So NOVA Education is the small department within NOVA that is really focused on extending the learning from the broadcast series into classrooms and into different educational settings through our content. And so we do that by producing resources like Sean mentioned. These are usually between 4 and 6 minute excerpts from our shows that are then contextualized with teaching tips, with discussion questions, with background essays and things like that. But we also do a lot of work beyond that to really create opportunities for community conversations around many of the topics that are covered in our films through creating virtual field trips, which are hosted by our outreach manager, Gina Veramo. And I think there are some of you here who've probably attended some of those. We also do a lot of community screening events as well. And really one of our core goals is thinking about how can we really foster curiosity in the sciences, how we can promote inclusive science communication and really amplify the voices of the next generation of leaders in STEM. And so you can find us on our website at pbs.org/nova/education. We're also available on all the major social media platforms. So you can find us on Twitter, Facebook, Instagram, and our YouTube channel where we host some of our webinars and other professional development sessions that we host for our audience. So today we're going to really be talking in the first half around 2 NOVA projects related to space science. The first is NOVA Universe Revealed, and this is a 5-part series about sort of some of the biggest moments that have defined our cosmos, which is currently available to stream on the NOVA website. And then we're going to talk about the Exoplanet Lab. And if you're not familiar with our NOVA Labs platform, this is our platform of science, games, and interactives. Again, everything that we do is free. But these are science games and interactives that are designed both for independent use, students can work on them independently, but also within a classroom. And they are web-based interactives and games. Students can log in using a PBS account, a Google account, or a Facebook account. And they're really, really great ways to create opportunities for inquiry-based learning and really innovative problem solving through these games and interactives that really make use of a lot of the science concepts and principles and tools that scientists use to explore these problems within their research and within the work that they do in labs. And so I'm really excited to also introduce Dr. Anjali Tripathi, who is somebody who has done immense work for NOVA. I'll just read her bio really quickly. Dr. Anjali Tripathi is an astrophysicist and the science ambassador for NASA's Exoplanet Exploration Program, based out of NASA's Jet Propulsion Laboratory, aka JPL. Anjali has explored the formation and evolution of planets, through research on protoplanetary disks, which are the sites of planet formation, and computer simulations of exoplanets losing their atmospheres. And she's going to show us a little bit of those really incredible computer simulations today. She is a research associate of the Center for Astrophysics at the Harvard, through Harvard and Smithsonian, and her research portfolio has spanned exoplanets and cosmology, dark matter searches, galaxy simulations, Milky Way statistics, as well as earthquake science, particle physics, and engineering. Committed to making science accessible for all, she has been an active science communicator for PBS, TED, and others. And really excited as well because Anjali has actually contributed to both the NOVA Universe Revealed and the Exoplanet Lab as on-screen talent and as an advisor. And so we're really excited to have her provide a quick primer really on exoplanet science and some of the really incredible things that she's been working on and will be sharing with you shortly. So I will pass it off to you, Anjali.
Thanks so much, Ralph. Could I share screen now?
Yes.
Great.
All right. There we go.
So hi, everybody. Greetings from sunny Southern California, where we do not have a snow day tomorrow, for better and for worse. Hopefully you can see my screen. If not, I hope somebody on the panel will give us a shout. But let's see. Just to check, you see it in presentation mode, right? Okay.
You're good. You're good.
All right, so I wanted to share a little bit about the world of exoplanets because, you know, when I was a kid, there were 9 planets, then we lost Pluto and we went down to 8. And now we talk about the thousands of planets we've discovered. And so in your students' lifetimes, we are going to continue to discover thousands of exoplanets. And I would imagine that we are going to find signs of life outside of Earth in their lifetime. So even though this is something that you and I maybe didn't grow up with as a subject, it's something that your students are going to have to get familiar with. And it's something that I think the NOVA resources provide a great backdrop for this. In the NASA Exoplanet program, we also provide resources like these beautiful posters, which you can go and download from our website. And so I just want to give you a brief overview of some of the science that we're thinking about, and you'll see this filter through in some of the resources we've all talked about. So let's get started. So when you hear exoplanets, you should just think of it as planets outside of the solar system. Exoplanet is short for extrasolar planet. And, you know, students often think about planets as just these balls of rock, but it's really important to think about a planetary system in terms of the star, where of course here our nearest star is the sun that we're all orbiting. And these exoplanets, you can imagine, then need to be found around other stars. So if you look at stars, you know, all over the night sky, it turns out that they're great hosts for exoplanet systems. In this one patch of the sky that was observed, and for all of those of you joining us from Arizona, this is a picture out there, you can see that the Kepler Space Telescope actually found a ton of planets. So each of those colored dots is a planet that Kepler detected. And the colors actually represent the different sizes of the planets. And the thing to note here is that those different colored dots don't necessarily correspond to planet types that we find within the solar system. Because, you know, while we are terrestrial sized and we have planets like the size of Jupiter, we're also finding these so-called mini Neptunes or super Earths, which are sort of intermediate between our small rocky planets like Earth and Mars and big gas giants like Jupiter. And if you look on the right side of this plot, you can see the number of planets that we had confirmed as of last week. If you go to exoplanets.nasa.gov today, you'll see that that number has increased 5 planets since I prepared these slides last week. And so you can see it's constantly evolving, which is pretty exciting. But the thing you notice is that you tend to get a lot of these big planets that you're seeing rather than some of the smaller ones. And part of that is a result of how we find the planets. In science, we often talk about the results and less about the methods, often because it's sort of work that's happened in the past. And I know a lot of you actually try to bring that process in, which is great. But it's very much the story of exoplanets at the moment, because you can see the vast majority of them, over 75%, were detected with the transit method. And I'll talk about what these are in a minute, but you can see that at the right, that if we look at how planets were detected over time in this movie, you can see that they were first found with the radial velocity method, which is that blue method. And you can see that it tended to find planets that were further out from their host star. So the distance from the star to the planet is represented in this graph on the x-axis by orbital period. And the size of the planet, they're giving it with mass. So not every planet, not all of those 4,900 are represented on that plot. That's only a plot of those for which we have a mass, which it turns out is a little bit of a holy grail in exoplanet science. But the neat thing you can see here is that each method is getting us to planets of different sizes. So if you want to find something like an Earth-like planet, you have to think about the technology you have available to you and the methods for how you can get there. So I mentioned that the first planets were found with the radial velocity method. And the idea there is just that, everything's got a gravitational force. And so here actually the star wobbles a little bit with the planet orbiting around it. And so if we actually measure that light coming to us from the star, we can look at the Doppler shift. And so that's why you see this wave of light becoming red or blue as the star moves and the planet passes in front of it. That, just that reflex motion of the star moving, even without the planet passing in front of it. I misspoke a second ago. You can see that reflex motion back and forth. And so if you don't see anything else in the system that could explain why that star is shifting, it might be because there's a planet. And so it turns out that the first exoplanet discovered around a sun-like star called 51 Pegasi b, which was discovered in 1995, was actually discovered with the radial velocity method. And this tends to be one of the ways that even if we observe something with transits and these other methods, we try to go back and make radial velocity measurements because it is so much a standard tool. But I mentioned transits, and you're all teachers, and maybe you'll appreciate this. This is one of my favorite pictures. This is a view of a school, I think in New York City in the 60s, and it's students making pinhole cameras with cardboard boxes to observe a solar eclipse. Of course, we have great solar eclipse classes these days, so these probably aren't used in your classroom much. But in the same way that a solar eclipse means, you block out the light from the star, it's very similar with the idea of transits. And in this picture, you can actually see transits of the International Space Station. So you can see it's a time-lapse image as it's going in front of the star, which is the sun. Because the idea is that a transit is when a smaller body blocks some of the light from the larger body, the star. And so this means that there are some systems where if you actually, if you actually see the light from the star blinking, you might say that maybe it's dimming because there are planets going in front of it. And so you can look for these really repetitive signals, right? Because the planets are going in orbit that could be attributed to the presence of planets. And so if we were to graph what that looks like, you can see that when the planet is passing in front of the star, the light decreases, right? For the rest of its orbit, you don't see any change in the brightness of that light. But as the star goes behind it and comes back around again, you'll see that you have these dips in brightness that we can attribute to the presence of a planet. And so these dips in the light curve, as we call it, are the main way that we found all of those planets that I mentioned before. And one of the interesting discoveries is called TRAPPIST-1. And so this video actually shows you what the light curve of TRAPPIST-1 looks like with an animation of the system. So you can see that they found so many dips in the light from the star that they had to attribute it to actually a series of 7 exoplanets around the star. And this star is not like the sun. It's actually smaller and redder, and it's an M-dwarf star for those of you keeping score. And it's just fascinating that this nearby star that you can see over a couple of weeks has all of these planets and these signals that they can disentangle. And finding exoplanets in these transit signals and using the radial velocity technique, I should mention, are both featured in that NOVA exoplanet lab. So It's something that students might feel like what they're doing is really disconnected from what we do in the lab. But actually, you know, my first paper that I published college was looking at transit signals. And so the neat thing about the TRAPPIST-1 system is that the planets that were found are actually just the right distance from the star to be warm enough where water would be liquid. If you were further out, you would be so far from the star that it's cold and water would be frozen and icy. If you were much closer in, water would be steamy. So we have this perfect area, we tend to call it the habitable zone, or you might hear a Goldilocks zone, that we think about as one of the conditions needed for life. With Valentine's Day coming up, I just had to put up this piece of art from our program. We have a series of exoplanet Valentines that your students can find at exoplanets.nasa.gov, like the rest of the resources I'll show you. But again, I mentioned the habitable zone because, again, that's sort of the holy grail for where we can hope to find planets that might contain life like we know of on Earth, because on Earth, we think of water as that essential ingredient. And so TRAPPIST-1, even though if you look at it, it's actually smaller than the distance between the sun and Mercury. And that's because, of course, around a smaller star, everything is closer in to get that warmth. But it's still a really exciting step in that search for life, because of course, step one, as you can see in the upper right, is find an exoplanet. Step two is check for the conditions of life. So maybe if you have liquid water, that'll help. And then we actually want to look at the atmospheres and see if we actually can detect the signs of life. So some of you may have heard about the James Webb Space Telescope, which launched on December 25th last year. And it's going to do a lot of great science, including some work on characterizing exoplanets and helping us with looking for the conditions of life and possibly biosignatures. And the way that's going to work is when you have these transiting stars, you know, you're getting the light from the star that you could measure with the spectra. But, you know, when the planet is orbiting in front of it, if it's just the right configuration, you can actually get the light passing both from the star through the atmosphere of the planet. And so that's why you saw those dark bands. And so you can actually see that the light from the planet can be backed out by subtracting the light from the star only to find out what is the chemistry of the atmosphere of that planet. And so this is a technique that we've done from the ground using really big telescopes. One is really called the Very Large Telescope. But this is something that the James Webb Space Telescope will actually be able to do. And one of its first targets actually will be the planets of TRAPPIST-1. It's one of these things that, you know, you'll be able to tell, is there oxygen, is there water? Because with those detection techniques that I mentioned before, those are just telling you if there's some physical motion. It's not necessarily telling you the composition. So there's a long line of space missions that have contributed to the study of exoplanets. Like I showed you, those colored dots at the beginning were observed with the Kepler telescope, which looked at one patch of the sky. The TESS spacecraft is actually surveying the whole sky, but it's going to look for near bright planets and near bright stars with planets around them that can then be followed up by James Webb Space Telescope and upcoming missions like the Nancy Grace Roman Telescope. So there's a lot going on in the world of astronomy and studying the universe. And I feel really grateful that we live in this exciting time when we can actually imagine getting answers to this question of, are we alone? So there's a lot of great resources out there. Again, everything I've shown you is on the website from my team, NASA Exoplanet Exploration Program. So that's exoplanets.nasa.gov. And you can see, again, you can find these travel posters, whether they're coloring book versions or in Spanish, to help complement the rest of the resources we find. So I'll stop there and turn it back over to the rest of the team.
Great. Thank you so much, Anjali. That was wonderful and such a great, I think, overview. And I really want to reiterate something that you mentioned, which I think is just so important about how in so many ways, this is sort of a field of space science that will really define so many of the new ideas, the new concepts, and of the new discoveries that many of our students will see in their lifetime. And so that's why it's so important for them to understand that science. Obviously, they're exposed to so much about exoplanets and a lot of the media they consume, every single sci-fi / like Marvel film has something dealing with outer space on another planet. And so I think there is a way in which even those media examples can help and grounding them in an understanding how this actually works and how we are actually discovering these exoplanets is such an important thing for us to be talking about in our science classrooms. So thank you so much, Anjali. So I'm going to just quickly transition to doing a fast overview of the Nova Universe Revealed series, as well as the Exoplanet Lab. And I'm just going to share my screen very quickly and hop back into this presentation. So as I mentioned earlier, the Nova Universe Revealed is a series that aired in November of 2021. It's a 5-part series that's now available to stream on pbs.org/Nova. Each of the episodes is about an hour long and looks at one particular area of the cosmos. And so there's Age of Stars, which talks about sort of how stars form and really takes a look at also at our sun, the Milky Way, Alien Worlds, which is our exoplanet episode, black holes, and then the Big Bang. And so I think what's really incredible about this series is it's very, very dynamic CGI. Just visually, it's very, very fascinating and interesting to watch. And it really helps to catalog some of the big moments that have happened within each of these categories of space science. Now, the PBS Learning Media collection, we're really happy to announce, has just been published. And it's now available to view on PBS Learning Media. So if you go there right now, type in Nova Universe Revealed, you will find this collection. The collection currently has about 5 resources. We have several that will be added over the course of the next week or so. But essentially what you'll find in this collection are video excerpts from the 5-part series, each within between 4 and 6 minutes. We also have a few media galleries, and each of these resources comes with teaching tips, discussion questions, and background essays. I would say if you think about consider the level of this collection, most of the resources meet the NGSS high school standards for Earth and space sciences, particularly focusing on the one around Earth's place in the universe. And so you'll find a lot of alignment there. And for each resource, you'll find a standard section which can tell you exactly if you are logged in, again, with your with a PBS Learning Media account, you actually see standards that are adjusted to your particular state, which can be a very, very helpful resource. So please check this out. Here's an example of what you might see in one of the resources. So this is our Exoplanet resource. And if you scroll down to each of these resources, you also will find support materials. And so I mentioned the teaching tips, but we also have some student readings that are very, very helpful. And I think these are especially helpful for students just because many students may not have as much background about these topics. And so the student reading really provides a good primer on what they need to know. There are also figures as well to help to explain some of the concepts that Anjali just discussed. You also find discussion questions and also some handouts. And these handouts are really great for independent practice and really provide another opportunity for a student assessment of their understanding after they've watched those videos. The next thing I'll quickly talk about is the Exoplanet Lab. And so this is really a really great way to really introduce students to exoplanet science, but through a very, very fun way. And so in this game, you essentially are playing a role in this Nova Galactic Resettlement team, and your job is to help aliens who are in desperate need of new homes by placing them and finding new exoplanets that sort of match their needs. And so it's a really fun way to get into understanding a lot of these ideas around how scientists currently are finding and categorizing the exoplanets. And so I'm just going to play the quick trailer, which is about 40 seconds, showing you sort of what the lab is all about.
Welcome to our Nova Space Center, ground headquarters for our Space Exploration Division.
Our mission is to explore the cosmos, discover planets beyond our own, and act as stewards of the Earth.
Let me be the first to congratulate you on your acceptance to the Novanaut program.
Based upon your sense of adventure and your can-do attitude, we've assigned you to one of our most important programs, the Galactic Resettlement Team.
You'll be the lead scientist, working to discover new homeworlds for displaced extraterrestrials.
Aliens. They need new homes, and you're gonna find them.
A couple of days ago, our lunar outpost received a distress signal.
You need to go investigate.
Ready?
All right.
Welcome to our Nova Space.
All right. Yes, and so in the Exoplanet Lab, So many of the concepts that Dr. Tripathi mentioned, transit modeling, radial velocity, using the color spectrum to sort of identify planet atmospheres. All of these sort of activities and concepts are modeled within the lab. There's also some really great analysis questions that students have to answer, where they have to categorize the planets based off of where they are in the habitable zone, based off of their atmosphere, and based off of all this data. So it really is a really rich way to apply for students to not only take this data and to use that data, but then to make inferences about that data in order to help out the alien species for each of the levels and missions of the game. In addition, we also have produced a lesson plan to accompany the Exoplanet Lab, which will make it much easier for you to figure out how to work this into your curriculum. And so in the lesson plan, you'll find quite a few support materials. The core objectives of this, again, are to model how they use transit and radial velocity data to determine an exoplanet, to determine the composition of that atmosphere, and then ultimately to create an argument about whether or not that exoplanet might work for that specific life form. And so again, you're really using a lot of data analysis here. You're using a lot of creating arguments, drawing inferences based off of that data. And in addition to that, we've also included some really great support materials to make sure that you have what you need to use with your students. And so there's an educator guide, which provides some tips for navigating through the game. We also have a teacher mode. And so this allows you as an educator to jump to different points in the game. So if you want to, say, demo one particular portion of it at the beginning of class, you can actually use this mode to hop into that particular portion of the game. And there's also a mission log, which is a really, really great resource. And I think Eric will touch a little bit about this following my brief presentation, but he'll talk about sort of how he uses that with his students to take notes and to also provide additional opportunities for independent practice and assessment of student learning. And so that said, I will pass this now over to Eric Fleming. Thank you all so much.
All right. So I just wanted to start with a couple things about me because these came up when working with the kids. I'm what you would call an elder millennial, meaning that I am a digital native, and working through this with students, there were some technology questions that came up. Because my classes in the 90s included keyboarding as well as some coding. I'm a geologist by training, so I can talk your ear off about how much I like salt, but dealing with a lot of the space stuff has left me in a lurch. And some of the questions that people submitted earlier about how to teach material that is kind of abstract and outside of your wheelhouse. So I hope that this can help with that pretty well. But moving from me on to my school, I teach at Tucson High, which is in an urban setting. It's a science and arts magnet school, so we're drawing students from across the Tucson Valley. We actually have the University of Arizona literally across the street from us, so I get to point that direction and tell my students they should be aiming for something like that. Our population is between 3,000 and 3,500 kids. Half of the students are on free and reduced school lunch, so we're a Title I school. And in the middle of the pandemic, we decided to go one-to-one on devices, which is where a lot of the technology issues have been coming up that we needed to deal with. So the resources that I used, I started off asking my students in my Earth and Space Science class, as we kind of pivoted away from Earth and towards space, what they were most interested in. And what they said across the board, black holes and other planets. Like that was nobody was interested in anything else. So that was great. I set up the Exoplanet Lab for my students, and there are the video clips available from the series about black holes, as well as some of the supplemental readings that I have highlight right there for you. So I gave my students heads up We're going to do all of this material. And can I get the next slide, please? And we were going to go one-to-one devices on day one, but we have issues. Very few students bring their computers daily. The complaint is that they are heavy. So I sent digital messages as well as spoken instruction. We have a block schedule, so I know with 48 hours difference, sending a heads up on remind is useful. But on the first day, I learned monitor and adjust is the way to go. So we played the videos on the first day, but some students did get to see what was in store for them. And that really did help out with student engagement on this. Can I get the next slide, please? So while we're doing the videos and the readings, I also had the textbook available for the students. In my textbook, I make a joke that Pluto was still a planet in it, but that's actually wrong. So it's more recent than I thought, but it is not the most exciting textbook. The students were not as excited as I was about the pre-release videos, but they did get to see the timestamp code on them. And I asked them for feedback, and you guys can read what's written on the right-hand slide there. That's honest feedback from students. And I just had one that I wanted to read out loud that is too large to fit in the space. But one of my students said, watching the video made me feel really small, but also opened up my mind to new things about space. And I was talking about black holes and everything. And that's just, I mean, that's where we want to be with this is, yes, it's going to make you feel small because these things are giant, but anything that opens up your mind just a little bit is going to be a great thing to move forward with. Next slide. So students saw potential on this, and we did the exoplanet lab. We did a little bit of it in class, and you can see I took a lot of shots over the shoulder. Students are kind of nervous. They're all moving sideways out of the camera's field of view when I was taking pictures across the tables at them. Next slide, please. And with regards to devices, I was noticing there were two major approaches that students were taking, and this kind of informs moving forward for me. But if they had a larger laptop or were kind of computer savvy, they would kind of work split screen on it. But a lot of students are really attached to using their phones for things. And I could convince them that consuming the information on the phone while typing stuff on the laptop worked better, because every time they tabbed away, it would be problematic on their phone. And they're digital natives, but they're still learning, and you may have to work with them a little bit on it. I posted the worksheet to have them fill out on our class Teams page, and I, the first time, did not mark it as read only. So some of them downloaded their own copy and went to work on it, but a lot of them were working on the live copy that I had put up. So I had to fix that because we're still going through this a little bit. Next slide. So these are some of my student work samples, and this is directly from the worksheet. They're filling out information, just getting some vocabulary down for things like orbital period or habitable zone. And I do like their brief bits there. If the orbital period is too short, we would burn, trying to make the connections about why that's a thing, and tying it into Kepler's laws was the next step that I had to do outside. But they also jumped into this. They can highlight things in different colors. They were putting everything down there and getting the hang of it pretty well as we went through our one-day block schedule on this. And then I told them the rest of it was for homework because there are a lot of levels involved. Next slide, please. And this is just two more student work samples, same thing. What I did get to see with this is there is some reteaching that had to be done with it. Between this planet A and planet B, they're asking which planet would be most likely to be warm as opposed to very, very hot. And while one student got the difference based on orbital period and being much closer to the star, I another student went for density on it. So I made sure that we went over this, and I put it in their assessment for later that they just took today. So I haven't gotten a chance to read it and see if the learning stuck. But I did like being able to pull everything up, digital format, kind of go through it down the line and check on all of the student learning that way. It's really nice and easy. And one of the things that came out of the pivot to online everything that I'm definitely going to keep. Next slide, please. And for some of this reteaching and kind of extending the learning, we had in Bringing Universe to America's Classrooms another interactive lesson that was exoplanets through Kepler's laws, and that used that TRAPPIST star there that you already saw a great animation for. The kids got to go through that. And there's also one on galaxies and the histories of the universe, because they really did get into this idea of black holes being at the center of different galaxies and how could this go on. And I'm seeing I have a question about grade level. My Earth and Space class is 10th and 11th grade mostly. So they're pretty good about jumping in and trying out different things. And I will say every time I do something with GBH and PBS LearningMedia, I am floored by the number of things that are available on the website and by how much they change. So something that's a couple of years old, I come back to it and I look at it, and there's new material, there's new checks for understanding. There will be supports for English language learners, which helps me a lot being from Southern Arizona. And there'll also be supports for people who need assistance with reading or other things like that. So it really is good to keep going back, and you just kind of look and check. And the best heads up I ever got was from Sean that there is a resource that was in the 3rd grade level that explained how eclipses happen better than anything else that I could have given my 15-year-olds. So you can get in there. It's a little daunting to see all of the different things that are available, but take a look because there's just some wonderful resources out there. Next slide. And that's me. So I'm going to toss it back for the talk about polar extremes.
Okay, thanks, Eric. So I'm back. Before we move on to polar extremes, I just want to say that the Universe Revealed collection right now has 5 resources, but within the next few weeks, it will have 10, so it will double in size. On the resource list that you'll be getting, all of them will be listed. So if you're interested in one of those, just keep checking back and it'll be there very soon. And that those particular resources in that collection, they all have student readings to help engage them, your students, with the phenomena, in addition to the handouts, teaching tips and discussion questions that most of the other resources have. Okay, so now on to something completely different, polar extremes. And this is a collection with about 15 resources, and it is about another NOVA series of 2 shows that is about the history of Earth, and in particular, the changes over time that have happened, the climate at the poles, and what that means about our planet's past. The films are hosted by Kirk Johnson. He's pictured there, and he is just awesome for making science accessible to kids. In particular, he's really, really good at talking about evidence to support the claims about Earth's history. And he doesn't just talk about the evidence, but really critically evaluates it, like why it's evidence and why it's better than something else. So he goes through that whole claim evidence reasoning and can illustrate that for your students in a really authentic way. In addition to video resources in the collection from these films, students can go on an immersive quest with another NOVA lab, the Polar Lab. In addition, we have some resources that are tied to Antarctic extremes, which takes students kind of behind the scenes in scientific research. Next slide, please. In the collection, it's a kind of wide variety of stuff. Since it's a lot about changing climate and throughout Earth's history, there are resources on adaptations of animals. Those fossils he's holding there are jawbones of horses, if you can believe it, so tiny. They answer the question of what ginkgo leaves can tell us about the levels of carbon dioxide throughout Earth's history. Next slide, please. In addition, we have resources on receding glaciers and what might be causing that, weathering of rocks and how that is a natural process for sequestering carbon dioxide from the atmosphere. In fact, that particular resource inspired us to expand and deepen our resource on the carbon cycle on another project, because, you know, usually we talk about the carbon cycle with the organic side, photosynthesis, respiration, decomposition in the soil. But, you know, the inorganic side is really, really important as well, if we really want to talk about both sequestering carbon and storing it and just the global carbon cycle. Next slide, please. And then, of course, in the collection, it's all about collecting evidence and really trying to piece this together, the story of Earth. So there's lots of fossils and things like that. Next slide, please. So besides the, like I said, besides the video resources we have in the collection, there's the NOVA Polar Lab and a lesson plan that goes along with it. And it's full of great videos, 360-degree videos, kind of make you feel like you're actually up there in the tundra. Carolyn, would you please play the videos so they can get a little feel for what the lab is?
You've probably heard something big is happening to our planet. Earth's climate is changing, and there's a lot hanging in the balance. But what does it all mean? And how does it compare to what's come before? It turns out the poles, the Arctic and the Antarctic, have quite a bit to tell us. Locked inside the ice and rocks at the top and bottom of the world are clues about our planet and its climate, where it's been, what's happening now, and where we might be headed. Welcome to the NOVA Polar Lab. I'm Caitlin at Polar Lab headquarters, and you're going on quite the journey. We've assembled a team of the best, top-notch scientists to guide you on your expedition. I'll be by your side, and we're all here to help. But it'll be up to you to find the clues and piece them together to answer some pretty big questions. Work your way from pole to pole, hopping from massive glaciers and frozen tundra to world-renowned laboratories. Watch videos, play games, solve puzzles, and earn stickers. Collect enough, and you'll unlock extra goodies. And keep track of your quest here, in your field notebook. Play the Polar Lab, and be part of the team racing to understand our planet.
Thanks, Carolyn. So you can see from that, both get an idea of what kids would be doing during the lab, but, and it looks like Nancy's used this before and she's put in that her kids are doing it tomorrow. That you can also get a feel for just the filming and the phenomena that they explore throughout these films. Next slide, please.
You've probably heard.
So also in the collection, there are a couple of resources that take videos from Antarctic extremes. And this is a series of videos that can be found on the PBS Terra channel on YouTube and on pbs.org. And Caitlin, who we just saw in the movie, and Arlo are hosts that don't just report on the science research in Antarctica, but they're actually embedded there and really investigate like what it's like to live down there and do work, do science, and kind of just dig in and give us a feel for how it is down there. I just have a few of these things represented. There's down on the lower left, there's a glacier that looks like it's bleeding. That's a lot, this is all chemistry. It's oxidizing iron and freeze point depression because of salty water. That thing that looks kind of like a torpedo on the bottom is actually a robot investigating glacier movement and stability. But the cool thing about it is that it's actually also being used to develop technology to look for life and investigate other worlds like Enceladus or Europa that have water oceans or are believed to have water oceans. And of course, down there they have the baby seals. And so we get to have a video about that. And you can't go down to Antarctica without visiting the penguins. And with that, I'm going to turn this over to George, who's going to talk about how his students dug into penguins in the Antarctica.
All righty. Good evening. Thank you, everybody, for attending. My name is George Hadaminas. I am a physics teacher at Richardson High School in Richardson, Texas. I'm currently in my 21st year of teaching here. I'm excited to talk about a project that I have introduced to my students, and it's called Home Sweet Home for Penguins, that is. And you're probably wondering, how in the world does penguins relate to physics? Well, I'm always looking for unique opportunities to bring these, these innovative approaches to activities into my classroom. And I had an opportunity to actually visit Antarctica as a polar trek teacher. I was there for about a month during November of 2017. And got to really appreciate a lot of the science and the environment that was happening within this very remote part of the globe. But it also got me thinking, and of course, one of the animals that I really just enjoy observing are penguins. And so one of the things I had thought about was, how can I bring the interest for penguins back into the classroom and tie it into a physics topic? So obviously the physics topic has to do with thermodynamics. And so what I wanted to do is get the kids thinking about how animals could adapt to very extreme temperatures. Could I have the slide, please? So what I did is I set up this project in 4 stages where the students would, do a very invasive type of research on penguins to get to know as much as they could about it. And then what I had them do is observe penguin behavior through webcams. There are a lot of zoos that have webcam observatories. They're very engaging, very interesting. And so what I did is I developed a log where the students would have questions in front of them that they would record. They would look for observations, look for things to write down, and just try to learn as much as they could about the behavior as best they could from like 30 minutes to an hour of watching on a webcam. And then they would take this information and create a habitat, to design a 3D model of a habitat, whether it was design an architectural blueprint, so to speak, or develop a 3D physical model of a habitat that would incorporate a lot of the characteristics that they observed by looking at the webcam. Could I have the slide, please? We'll try to get through this fairly quickly. So this is obviously a slide where I have the students looking at a lot of the materials. Of course, there were books that I arranged through the library, but then also there was the Polar Extremes resource. Very, very helpful. It actually brought back a lot of memories for me, and it was something that I could supplement as the kids were engaged in the videos and going through the different activities and tasks. Slide, please. This is an example of a screenshot from a webcam. There are actually quite a few out there. It's just very interesting to see penguins, how they interact with one another, and it's very easy to spend 30 minutes, let's just say, glued to a computer screen watching penguins waddle back and forth. Next slide. This is an example of an observation log that I created for my students to give them an idea of questions that they would ask themselves as they were looking or observing the webcam. I know it's a little hard to read, and if there's interest, I would be glad to share copies of this. But you know, when you set a student in front of a computer and you really don't give them any guidance, there really isn't a guarantee that they're going to come back with something constructive. So what I wanted to do was model some questions that they could in turn be looking for as they were observing the penguins through the webcam. Next slide. Then what I wanted to do is have each group share their observations on a almost like an electronic bulletin board. This is one example. It's called Lino, but I use Padlet a lot. But one of the things I always try to do is expand my applications into various technologies. You know, once I hear about something, I always want to give it a shot. Let's see how my students respond. And who knows, there may be something bigger and better by trying these things out. Next slide. So we got to the point where we were ready to do the modeling of the habitat, and this is when COVID struck. It hit us pretty hard. We went into virtual learning, basically shut down the whole idea behind the project. But we are fortunately coming back. We are in school, face-to-face learning. And I am in the process of presenting it to my students, and I hope to eventually see the end product. It's something I'm really excited about, and I'm hoping my students will see the same thing. Next slide. One of the things I always like to do when I give these kind of talks is not only talk about my experiences with a particular activity, but also provide extensions. You know, where could you take this further for some kids? I know that one of the questions that was asked prior to this webinar had to do with differentiation. And I know differentiation is something that our administration really focuses on. And it's something that I think is really important to address the diverse array of learners that you have in a classroom. Well, for this project here, you could easily take the project in chunks, and then for those that were more adept, more creatively inclined, could take it all the way to the end. But then there's also, oh, Palmer Station. Yeah, it is. It's very interesting, all the research that's happening there. But this is one example of an extension, which is citizen science opportunities. I understand that this was passed. This is past date, but there are some ongoing opportunities, and I would glad to share them with you as well. But it's something to engage your kids with in learning, you know, not only about penguins and how they interact with one another, but more importantly, how they play a bigger picture in the polar extremes. It's very interesting, the science that's happening here, and projects like these provide students opportunities to learn and engage more on a really interesting subject. I believe that's it. Thank you very much for your attention.
Okay, we'll do a really quick wrap up here. Just a reminder that most of the resources that we were talking about tonight can be found on pbslearningmedia.org. and they're all free. So please go check them out. Next slide, please. Just a few other things that you might want to check out in particular. Making North America is another NOVA collection hosted by Kirk Johnson, and it's about how our landscape came to be. Decoding the Weather Machine, another collection from NOVA, and that just has resources that lay out the evidence for climate change really, really nicely. So if that's something you need, check that out. Bringing the Universe to America's Classrooms is not a NOVA collection. It's a different kind of resources for K-12 students that address Earth, space, and physical science. Media resources that are meant to actively engage kids with phenomena and have them engage in practices. Next slide, please. And Ralph will tell you what's up next month.
Yeah, so really excited. So on Tuesday, March 8th, we'll be doing a follow-up webinar where we'll discuss some of the new collections that really focus on how we can talk about these issues that are really at the intersection of science and society. And so we'll be talking about Beyond the Elements, which is our three-part chemistry series, which really talks about reactions, and particularly the reactions that have really shaped human society. The cannabis question, which is one of our newer collections, looking at, which is based off of our film, The Cannabis Question, which is a 1-hour film that really examines sort of what we know about cannabis, how we can have sort of discussions with students about its impact, obviously, with legalization happening across the country. It's really, really important that we empower students with knowledge, with scientific knowledge and accurate knowledge about cannabis. And so this is a really great resource that provides opportunities to talk about the endocannabinoid system, cannabis's impact on the brain, sort of the criminal justice system as well, and how that has had an impact on sort of our understanding of cannabis. And then our last thing that we'll be talking about is Misinformation Nation, which is a digital series from NOVA. It's a 4-part series that really examines sort of how misinformation spreads and how students can be more prepared. So this is a really, really great collection that provides a lot of digital media literacy resources that will be really helpful for students who are navigating a digital world and really sort of empowering them with the knowledge to make better decisions about the type of content they consume online. So please make sure to join us for that. We'll also have some really, really great sort of commentary from educators who are using these resources, and also hear from some content experts as well, talking about these 3 topics. So really excited to see you all there soon. Thanks.
Wow. Thank you very much, everybody. So we're at the end of the formal presentation, going to move into answering some of your questions. Maybe they're in the chat. If not, we can pull certainly from the questions that you submitted ahead of time. We are always striving to make our sessions more worthwhile and worthy of your time. So we ask you please to complete a brief survey. Here's the link. Angelica will also be posting it in the chat. The survey will be open for a week, and you're welcome to download, after completing it, a certificate that acknowledges your participation this evening. So I want to thank Ralph and Sean, in-house staff people at GBH, Anjali Tripathi from NASA, Eric and George, 2 hardworking educators. This has been a wonderfully rich presentation, and I appreciate all of your attention, and thank you to all of you. So I think I'm going to stop sharing my screen, and if the presenters want to come back on camera, and we can, let's see, I thought I was going to stop sharing my screen. Let's see what happened here. Well, let's see. Here we go.
It looks good, Carolyn.
All right, what do you see now? I don't see anything. I see.
Yeah, you're not sharing your screen. I think they should just see us now.
I'm not sure. Okay, good. All right. All right, great. So if anybody has noticed anything in the chat that you want to respond to, or Angelica could call things out. This is your time. So let's see what people want to know more about. I've lost the chat. My view has changed when I stopped sharing. Something weird happened. I don't want to mistakenly close out the meeting. So I do have to rely on the presenters to call things out, Angelica, or the attendees to put something in the chat and have you respond to it.
Somebody just dropped in the Q&A if the labs save student progress, and they do. You just have to make sure that the students are logged in, and they can use Google accounts for that or make an account on PBS LearningMedia. But that was a key one for some of my students who got some work done and then had to redo it.
And I'll also add that Google Classroom integration does exist both for PBS LearningMedia in general, as well as through the labs as well. So this is a really helpful way to ensure, again, that you can very easily send any of these to your students through Google Classroom, but the plugin is available and accessible on both the labs platform as well as on PBS LearningMedia.
And I see a question in the chat about the James Webb Space Telescope, so I'll just take that one quickly. So like I said, James Webb Space Telescope, JWST, or Webb for short, just launched. It recently got to its final home about 1 million miles away at L2 very recently, so that's very exciting. And JWST is going to be great for exoplanets because fundamentally, it's going to be able to tell us about what those exoplanet atmospheres contain, some of those chemical signatures with looking at the spectra of the planets. So I'd say that's its main contribution that we're most excited about. But JWST will also, it has the capability to actually do some direct imaging, so blocking out some starlight from the stars and actually looking to see if you can actually see the planet directly, although that's a technique that will be used a lot more by future missions. And then actually, rather than looking at the adult fully grown planet stages, you'll actually see the early stages of forming planets and protoplanetary disks and debris disks, because it's looking at infrared light. And that's where the dust and material in the disk in the young star gets heated up, and we can actually see that shining out at these infrared wavelengths. So yes, lots of science to come with JWST.
I'm going to throw out a question that was submitted with the registration. How can we use the current flat Earth craze to engage students to debunk it on their own understanding journey? Who would like to tackle that?
Yes, this is so this is actually a great topic for our next webinar in March. So one of the videos actually from the Misinformation Nation collection actually opens up with a discussion around flat earthers and sort of talks about really sort of why people believe misinformation and how people will sort of deny and refuse to sort of all the available evidence in front of them once their beliefs are really set. And so we do talk about that quite a bit in that collection. So definitely recommend that. But obviously, I think a key thing, any discussion around sort of conspiracy theories, particularly related to science, I think it's really key to focus on really what are the digital media literacy skills that we can build on and enhance on with regards to understanding sources, with regards to being able to decipher between facts and opinion-based sort of journalism. And so I think that's always a great opportunity to do that, just because that is something that I think it's one of the easy sort of conspiracy theories to tackle and to debunk, but we will talk a lot about that, particularly in the Misinformation Nation series and in some of the digital media literacy resources produced for that collection as well.
All right, we're winding down. Are there any final thoughts or things that you want to respond to from the presenters as we are in our last minute or so?
One comment I would just make, because I see a couple questions in the chat. Also, we got a few of these beforehand about folks getting into science communication or pivoting careers. I know a few of us on this panel have had some pivots in our careers, certainly I actually, one of the hats I wear at JPL is I'm part of our government affairs team, and I used to work in the White House. And so it's something that I think happens a lot more frequently than we might tell the story of. And so that's something I encourage you to share with your students. And I think there are ample examples you can find, including the folks here, about that with some resources.
Okay, thank you again to all the presenters and all of you who logged in. You will get an email that will come from Zoom tomorrow with the link to the recording, a link to the resources, and the slide presentation. I know that George and Eric, I don't know if you've shared your contact information, if you want to do that, or if you're on a social media platform, if people want to get in touch with you, that would be great. We will have the registration link for the March 8th webinar available in a couple of weeks, and that will come out to you just by virtue of you being at this webinar. We'll make sure you're on our mailing list. So, okay, 8:15, guys. Thank you very, very much. Wonderful job. I appreciate it. And hope to see you next time. Have a nice evening. We'll keep the chat open for another minute. Thank you very much.